Hello everyone. This is going to be our last lecture of Logic Design course. I hope it was a useful course for you, including the labs and the homeworks and the lectures itself. I know during this pandemic session we had some difficulties. We're still having some difficulties with the online teaching and so on. I hope it was useful in a way that you can use this knowledge for your future career. I hope it will help you throughout the academic or industrial work for the later years. So if you have any questions or if you want to discuss something related with the logic design, digital design, embedded systems and so on, feel free to contact me anytime. So today I am going to talk about asynchronous sequential design. This chapter is actually divided into two. The first part is the analysis part, and the second part is the design part. But we are not going to cover the design part. We are just going to cover the analysis part, because design part is a huge chapter and there are lots of details over there, which I don't want you to get into that trouble at the end of this term. So I'm just going to skip the design part and you're not going to be responsible from it. So let's give a start and let's talk about asynchronous sequential design. Now in chapter 4 we have seen combinational circuits that we have shown that whenever we have got a new input, the output changes based on that input. We can derive using the K-maps and find out the expression and design the logic circuitry. And in chapter 5 we have seen synchronous sequential circuits, which they are reacting based on the clock, not just with the input. So when we ask about the difference between asynchronous and the synchronous design, what you can say is synchronous designs works with the clock, it synchronizes with the clock, the data, but with the asynchronous one, it doesn't synchronize with the clock and it only changes the internal state after the input is changing. But with the synchronous one, present state specified by the flip-flop values and does not change if the input changes while the clock pulse is inactive. Now, based on this knowledge, we are going to dive into the asynchronous sequential design. You might ask, what's the difference apart from the clock? The main difference is, yes, it's the clock, but on the other hand, we have to consider the internal states when the inputs are changing, and because the inputs might arrive at a different time as they are not clocked, we might have some problems over there. So the memory elements in the synchronous sequential circuits are clocked flip-flops, as you already know. But with the memory elements in these asynchronous sequential circuits, either they are unclocked flip-flops like the latches or time delay elements. And the memory capability of a time delay device depends on the finite amount of time it takes for the signal to propagate through the digital gates. So that time delay depends on the finite amount of time, which we know as the propagation delay. And asynchronous circuits, they are harder to design due to the potential instability issues and their timing problems involved in the feedback path and so on. And as we already said, the change of the state occurs immediately after the input changes. So when we are designing asynchronous sequential circuits, we need to be very careful that each new state keeps the circuit in a stable condition even though the feedback path exists. So let's get into the slides. This is chapter 9 in the Mano and Giletti's book, and you will find similar definitions over here as well with the synchronous sequential circuits and asynchronous sequential circuits. Now we can say that asynchronous circuits are useful in variety of applications, because you might ask, if synchronous ones are better, why don't we use why don't we just use the synchronous ones? Asynchronous ones are good in various applications, like the speed of the operation is important. So you want a digital system which responds very quickly. So you don't need to wait for the clock. So whenever the input changes, you have the result. Or in other cases, economical to use. They're small independent systems. They just require few components without a clock generator and clock trees and the clock wires around. And two synchronous circuits with independent clocks need to communicate with each other. So that's another problem. That's why we might prefer to use asynchronous circuits. So in general, we can say that based on the applications and the needs of the design, you might want to use synchronous or asynchronous design. So in this chapter, we are just going to consider the asynchronous part, which we haven't done it before, and we'll see how we can interpret these and how we can deal with it in general. The block diagram of asynchronous sequential circuit, let's start with that one. Now, if you do remember from the combinational circuits, what do we normally have? We have got a combinational circuit, and for that circuit, we have got a set of inputs coming in, and we also got a set of outputs coming out. So we can say x1, x2, xn, and let's say the output is z1, z2, zn. On the other hand, we also have some feedback path, and of course we have got some delay element in that feedback path. We can have more and more which are coming out and going in, and each of them has got their own delay elements. In this case, let's say this is y1 and this is yk, and the feedback that is going in as a present state, it's small y k and small y1. So k is actually the secondary variables or the present states that we are representing in this case. And the k on the over here, it represents the excitation variables, which are the next states. And the delay elements can be visualized as providing short-term memory for sequential circuitry. And in a gate type circuit, the propagation delay that exists in the combinational circuit path from input to the output provides sufficient delay along the feedback loop so that no specific delay elements are actually inserted to the feedback path. So we can just assume that propagation delay is our delay element. Now, for a given value of input variables, the circuit is stable if the present state is equals to the next state. So in the end, we can say that the present state I have to be equals to next state I for all I equals 1, 2, up to k. Now, to have a proper operation, asynchronous circuits must be allowed to attain a stable state before the input is changed to a new value. This is really important to ensure a proper operation. Asynchronous circuits must be allowed to attain a stable state before the input is changed to a new value. And because of the delays in the wires and the gate circuits, it is impossible to have two or more input variables change at exactly the same instant of time without an uncertainty as to which one changes first. Therefore, the simultaneous changes of two or more variables are usually prohibited. Now, In asynchronous sequential circuits, we normally consider the circuits with fundamental modes of operation. So what is that fundamental mode of operation? The input signals change one at a time, and when the circuit is in a stable condition, that means we have got fundamental mode of operation. Now let us consider an example to interpret the theoretical definitions with some meaningful expressions. So example sequential circuit is given to us with AND gates and NOR gates and couple of inverters. Let's write down their expressions based on the inputs and the outputs. If we consider the first part of the circuit, the first output of the OR gate as Y1 and the feedback path as small y1, we can write an expression as follow. So the first AND gate is AND and the feedback of y1, which is small 1. So we can say that x dot y1, or the second AND gate is x prime, and let's say this is y2. So x prime y2. Now for the second OR gate, as we already said, the output is y2. Then we consider that AND gate, which is already found as x prime y2, or that AND gate is y prime y1 prime x. So x y1 prime. Now these are our two output equations that we consider in this asynchronous sequential circuit. By using these equations, we can derive a transition table. The transition table, they look like the Carnot maps, but they're a little bit different over here. So in this case, we have got two inputs where x is either 0 or 1, and we have got small y1, small y2, which represents our feedback or the states for the present state, and they can be 0 0, 0 1, 1 1, and 1 0. And actually this is going to give us the next state expressions. So if we start with the first equation, let's write down the y1 values when x is 0. When x is 0, y1 is going to be 0 dot y1 is going to be 0, and that's going to be 1 dot y2. So y2 is 0, that means that's going to be 0, so this is 0. Then when y1 is 0 and y2 is 1, so y1 is 0, x is 0, this is going to be 0, or x is going to be 1 because it's x prime, and y2 is 1 in this case, that means that's going to be 1. And we repeat the same thing for 1 1. So this is y1 is 1, x is 0, this is going to be 0. Then y2 is 1 and x is going to be 1 because of the x prime, that's going to be 1 as well. And the last one, as y2 is 0, that's going to be 1 0, and y1 is 1 and that's going to be 0, so they're both 0. When x is 1, y1 is 0, so this is going to be 0 because that's going to be 0 as well. When x is 1, that's going to be 0 because that's always 0, and that's going to be 1 dot 0 because y1 is 0, so that means that's going to be 0 as well. When y1 is 1 and x is 1, this is valid, so this is going to be 1. And when y1 is 1 and x is 1, this is also valid, so that's going to be 1 as well. So the blue colored values are representing y1 next state. And let's do y2 now. When y2 is x is 0 and both are 0, now this is going to be x is 0, y1 prime, it's going to be 1, but this is 0, so that's going to be 0. And y2 is 0, and that's going to be 1, so that's going to be 0 as well. So this is 0. Then y2 is 1 over here, and that's going to be 1 because of the x prime, so that will be 1. And over here as well, as y2 is 1 and we have got x prime, that's going to be 1 as well. y2 is 0 over here, y1 is going to be 0 as well, so that will be 0. Then when x is 1, y1 prime, it's going to be 1 because y1 is 0, y1 prime is 1. When x is 1, y1 prime, that's still 1, so that's also valid. But then y1 is going to be 0, y1 is going to be 0, y2 is 1, but x is 0 over here, so the last two, it's going to be 0 as well. So the blue ones are representing the y1 next state values, and the red ones represents the y2 next state values. Now, what we can say about this transition table is we have got the internal states and the inputs combined together, and we call that total state. So the total state is internal state and inputs combined. Stable total states are y1, y2, x is going to be equal to, so to find the stable states, that means on the present state and the output state, they have to be equal. Now the present state is 0, output state, so the next state is 0, 0, that is stable. And present state is 0, 1, then the next state is 0, 1, so that one is stable when input is 1. Then the present state is 1, the next state 1, 1, so that is stable when input is 0. And the present state is 1, 0, and the next state is 1, 0 when input is 1. So we can say that 0, 0, 0, 0, 1, 1, 1, 1, 0, and 1, 0, 1, those are our stable total states. And the rest is the unstable total states. So in this case, it's going to be 0, 0, 1, 0, 1, 0, 1, 0, 0, and 1, 1, 1. Those are our unstable states. So normally on the transition table, to show the stable states, we use circles. So those green circles are representing the stable total states. This example showed us how we can derive a transition table and find out the total stable states from the transition table for an asynchronous sequential circuit. On the other hand, we can also use a flow table to represent these transitions. Flow table is similar to the transition table, but rather than using the binary values for the present states or the next state, we are just going to use some symbols or the characters. So let's draw this over here. Let's say flow table for this transition table. As I said, they are exactly similar. We have got 0, 1 for x, y1, y2, and rather than having 0, 0, I'll have a, b, c, and d. And now 0, 0 is a, 0, 1 is b, 1, 1 is c, 0, 1 is b, 1, 1 is c, 1, 0 is d, then a and d. And again, to show the stable states, we just circle the ones that the present and the next state are equal to each other. That means we have got stable states, and this is also known as primitive flow table, because primitive flow table has one stable state in each row. Now we are going to do another example by using a flow table. The example given over here, there is one feedback path which is y, and there are two states A and B. They can be 0 and 1, and we have got two inputs x1 and x2, and we have got one output which is annotated next to our states. So in order to derive the state table and the output table for this example, or the transition table, I am going to draw the transition table directly from the flow table. Now the transition table, we have got similar to the flow table, 0 0 0 1 1 1 1 0, which represents x1 and x2, but we have got one feedback path which is y, and that is represented with a and b. So we can say that a is 0 and b is 1. I'm just assigning the binary values over there. The given values are for a, if it's going to be 0, this is going to be 0 0 0, and that one is 1. I'm not writing the outputs, I'm just writing the states. And then we have got 0 0 1 1. This is our transition table. We can also derive the output table, which we just need to consider the outputs. Again, 0 0 0 1 1 1 1 0. That's for x1, x2, and y 0 1. And our outputs are 0 0 0 0 0 0 1 0. Now we have got our transition table and our output table. To specify the stable states, we just need to circle, because the present is 0, next is 0, these are stable ones, and present is 1, next is 1, these are stable ones. Now, how are we going to derive an expression for it? Like we were doing it with the Carnot maps, we can combine the ones and find out an expression for y. So this is going to be the 1, which is x1 x2 prime, and we have got another one which is y x1. Now we have got two expressions, so we can say that y is x1 x2 prime or x1 y. This is the next state expression, and we can represent the same thing for the alp. We can do the same thing, but over here we just have 1, so that's going to be x1 x2 y, and that represents our output expression. And based on that, we can draw our logic circuitry. So our next state equation is given as x1 x2 prime or x1 y, and our output is given as x1 x2 and y. Let's derive logic circuitry. We have got an AND gate, two of them, and then there is an OR gate, so those are connected. x1 is directly going in to one of these gates, and two of these gates actually, for both of them. Then we have got x2, and that is going with an inverter to the AND gate. So that is our first part of the equation. On the other hand, we have got the y, which is the output, and that y is going to be fed it back, which is small y, and that y is also going in for the z output. So we need to have the z somewhere here, which represent the y, and we have got x1 and we also got x2. This example has showed us how we can derive from primitive flow table a circuit diagram. The next thing that we are going to consider is the race conditions. In asynchronous sequential circuits, we do have race conditions. The race condition is actually when we have got two or more binary state variables change their values response to the change in the input variable. This might be because of the unequal delays encountered a race condition and may cause the state variables to change in an unpredictable manner. For example, if the state variables must change from 00 to 11, the difference in delays may cause the first variable to change sooner than the second one. So this will result that the state variables change in the sequence from, let's say, 00 to 10 and then 11. Or maybe the second variable changes sooner than the first one, and then the state variable will change from 00 to 01 and then to 11. So when we consider these race conditions, we can say that state variables must change from 00 to 11. And as we already said, because of the delays, this may cause the first variable to change sooner than the second one. So that means it can be like 00 and then 10 and then 11. Or it might be the case that the second variable changes sooner. So it can be 00 or 01 and then 11. So these are all possible because we don't know the order in advance by which the state variable change, and we don't know the delay over there. So when we consider the race conditions, we have two types of race conditions. The non-critical race. So if the final state that the circuit reaches does not depend on the order in which the state variables change, this is known as non-critical race. But if it's possible to end up in two or more different stable states, depending on the order which the state variables change, this is known as critical state. And for proper operation, asynchronous sequential circuits, the critical races must be avoided. Let's do an example. Let's say we start with a total stable state, and we have got y1, y2, and x is equals 0, 0, 0. And change the input from 0 to 1. The state variables must change from 0, 0 to 1, 1, which defines a race condition. The transition table, this is 0, this is 1, 0, 0, 0, 1, 1, 1, 1, 0. So x, y1, y2. Now let us consider the case where we start with 0, 0, then when the input is changes, for each state we have got 1, 1. The stable state is where it is 0, 0. And the possible transitions that we can have is actually those. So from 0, 0 we can directly go to 1, 1. Or from 0, 0 we can go to 1, 0 and then 1, 1, or 0, 1 to 1, 1. So there are three possible transitions that the state variable may change. And in the end, the final total state is 1, 1, 1. Or let us consider another example where we have got a transition table 0, 1, so 0, 0, 0, 1, 1, 1, 1, 0, and y1, y2, and x. So we start with 0, 0. We can maybe, changing the input, we can go to 1, 1, or from 0, 1, we have got another stable operation which is 0, 1, or from 1, 1 to, we can go to 0, 1, or from 1, 0 to 1, 1. Now in these cases, we have got the stable states from 0, 0 and 0, 1. What we are actually having is, we can go from 0, 0 to 1, 1. We can go from 0, 0 to 0, 1. Or we can go from 0, 0 to 1, 0. And then 1, 1. And then 0, 1. So in the end, the final state is 0, 1, 1. So these are non-critical race conditions. Now, if we consider the critical race conditions, and as we already said, it is possible to end up in two or more different stable states depending on the order which the state variables change. So we start again, total stable state as y1, y2 and x is equals 0, 0, 0, and change input from 0 to 1. So the state variable must then change from 0, 0 to 1, 1. Now, if we consider the transitions, let's say 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, and we have got stable states 0, 0, 0, 1, 1, 1, and 1, 0. If they change simultaneously, the final total stable state is 1, 1, 1. If, because of unequal propagation delay, y2 changes to 1 before y1 does, then the circuit goes to the total stable state to 0, 1, 1 and remains. If, however, y1 changes first, the internal state becomes 1, 0 and the circuit will remain in internal state 1, 0, 1. And this is critical race condition. So the possible transitions are 0, 0 to 1, 1, 0, 0 to 0, 1, or 0, 0 to 1, 0. So as you can see, we have got different total end states for different conditions. And we have to avoid that. So the race is critical because the circuit goes to different stable states depending on the order in which the state variable change. We can also have another example where 0 and 1, 0, 0, 0, 1, 1, 1, 1, 0, and y1, y2, and x. So start with 0, 0, 1, 1, 1, 1, 1, 1, and 1, 0. Now, the two possible transitions result in one final state, which is 1, 1. So 0, 0 can be 1, 1. 0, 0 to 0, 1 can be 1, 1. But 0, 0 to 1, 0 is not going to end up in 1, 1. So the third possible transition goes to a different state, and this is also critical race condition. Now, how can we avoid these race conditions? There are a couple of ways of avoiding the races. One of them is making proper binary assignment to the state variables, so that the state variables must be assigned to binary numbers in such a way that one state variable can change at any time when a state transition occurs in the flow table, or we can avoid them by directing the circuit through intermediate unstable states with a unique state variable change. This is known as oscillation, which we are going to see next. Consider the unstable circuit given in the figure. So let's derive the next state equation for it. Y is equals, we have got a NAND gate which is x1 small y NAND and x2. Then using De Morgan, we can have x1 prime or y prime x2. And we can open that up as x1 prime x2 or x2 y prime. So this is our next state equation. Now the question is, what happens when x1 x2 equals 1 1? Let's derive the next state K-map for it. We have got y x1 x2. Now x1 prime x2 is over here and x2 y prime is over here, and the rest is 0. And now let's identify the stable states, which is present state is 0, next state is 0, present state is 0, next state is 0, present state is 1, next state is 1. So these are our stable states. And the question asks, what happens when x1, x2 is 1, 1. Now over here, as you can see, we have got 1 and 0. So when the present state is 0, next state is 1. And when the present state is 1, next state is 0. This is actually showing us that when the input is 1, 1, we have got no stable state. So in that case, the next state is not equals to present state. And what is happening over there? The internal state keeps toggling until input changes again. And this is known as oscillation or the cycle. And this is what we observe from the unstable asynchronous sequential circuits. And the cycle may be desirable if you are building an oscillator or a clock generator. Otherwise, it might be problematic. Now, the next thing that we are going to consider are the latches. The traditional method of asynchronous circuits configuration has been with the components that are connected to form one or more feedback loops. So when digital circuits are constructed with electronic components, it is convenient to employ SR latches as a memory elements in asynchronous designs. I don't know if you do remember SR latch from chapter 5, sequential circuits, but I'm going to make a quick revision on that. Now, SR latches, we have got NOR gate and we have got a reset input, a set input, and the output Q and output Q bar. So the output on one side will go in and output of the other side will go in as an input to the other one. This is actually an asynchronous circuit. As we already said, we just need to have a feedback and the present and next state. So Q is actually can be Y, and the feedback coming in is actually small y. And if we go back to the chapter 5 and revise the characteristic table of SR latch, what we have is when 0, 0, we have got no change, so we are holding. When it is 0, 1, we are resetting, so it's 0. When it is 1, 0, we are setting. And when it is 1, 1, it's undefined. It's not a valid state. If we want to write an expression for it, we can say that y is equals s plus small y prime, as this is our NOR gate, or r, and then that will be primed. So s plus y prime is actually representing q prime over there, or r prime. And if we rewrite this expression as these two are going to cancel each other, that's going to be s plus y dot r prime, which is equivalent to s r prime or y r prime. And this is our SR latch expression for asynchronous circuit. Now we can derive the transition table based on that. So we have got y, which is 0 and 1, and SR, which is 0, 0, 0, 1, 1, 1, 1, 0, and SR prime, it's going to be 1, and y r prime. So y r prime is on the first two, but it's going to be y, so it's over here, and the rest is zeros. Now when we identify stable states, the present state is 0, next state is 0, present state is 0, next state is 0, and the present state is 1, next state is 1. These are all our stable states. Now from the transition table, we can observe that going from SR11 to SR00 produces an unpredictable result. If S goes to 0 first, the output remains at 0. But if R goes to 0 first, then the output goes to 1. In normal operation, we must make sure that ones are not applied to both S and R inputs simultaneously, because it's an undefined state. This condition can be expressed by the Boolean function as SR equals 0, which is ending S and R must always be 0. Now, coming back to the excitation function we have observed over here, when we OR the Boolean expression SR prime with SR, the result is a single variable because we can take out S and we just have R prime plus R. That will be cancelled and we'll end up with S. So from this, we can say that SR prime is going to be equal S when SR is equal 0. Now we can say that SR prime is going to be equal S when SR is equals 0. Therefore, we can rewrite the excitation function, which we have found as y is equals SR prime YR prime, as y is equals S plus R prime Y when SR is equals 0. So before we do any design using SR latches, we must check if SR equals 0 and we can use the reduced formula. Otherwise, we have to use the original formula. And this is the way of designing circuits, asynchronous sequential circuits using SR latches. And these are all explained in the slides as well. There's also a NAND implementation, like we have done it in the chapter 5 as well. You can consider that. And only the equation is going to change and the polarities. Derivation of latch-based circuits: derive a transition table for the problem at hand. Derive a pair of maps for SI, RI for each I, 1, 2, 2 up to K, when we have got next static outputs as 1, 2 up to K, using SR latch excitation table. Simplified, draw the logic diagram using SR functions. Right, let's do an example related with the SR latch implementation. Implement using an SR latch. The expression is given for us, which is y is equals x1 x2 prime or x1 y. Now the first thing to do is to derive the transition table. The transition table, it says for the equation x1 x2 prime. x1 x2 prime is over here on the table, and then we have got x1 y. x1 y is where x is 1 and y is 1 as well, which is somewhere over here, and the rest is 0. Now let's take into circles the stable states. Present state is 0, next state is 0, present state is 0, next state is 0, 0, and present state is 1, next state is 1, and we have got all these covered as stable states. If you do remember from chapter 5 the SR excitation table, if you don't, I'm just gonna review it over here now. So as we already said, SRQ is our characteristic table, which is 0, 0 will be hold, 0, 1 is reset, 1, 0 is set, and 1, 1 is undefined. This is the characteristic table. The excitation table is we have got the present and the next, and we have got SR inputs. So 0, 0, 0, 1, 1, 0, and 1, 1. Now, how can we derive the excitation table? When the present is 0 and next state is 0, either we are holding or we are resetting the output. So S is 0 in both conditions and reset is changing. So that means that will be 0 and reset is X. Then we consider the next line where present state is 0, next state is 1. This is the only case where it's setting the output. So when it's setting the output, this is going to be 1 and the reset is going to be 0. And 1, 0, that means it's resetting the output. That means set will be 0 and reset will be 1. So when both are 1, either it's setting or it's holding. So when they're setting or holding, so S is changing but R is 0. So S is X and R is 0. And we have got the excitation for SR. Now what we need to do from the transition table, we have to derive S and R input equations for the latch. Now we need two Carnot maps, one for R, one for S. So 0, 1, 0, 1, this is Y, this is X1, X2, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, and this is Y, this is X1, X2. This is for R and this is for S. Now, how are we going to derive this table is the important point over here. As the transition table shows us the present state and the next state, we can easily derive S and R values from the excitation table. Now, let's change the color first. The present state is 0, next state is 0. So the present state is 0, next state is 0 means S is going to be 0, but R is going to be X. So 0, X. Then the present state is 0, next state is 0. It's still the same case, 0, X. Then the present state is 0, next state is 0. That's still this case, it's 0, X. Then we have got the present state as 0 and next state as 1, which is going to be the second row, which is 1, 0. Then when present state is 1, the next state is 0, it's 1, 0. So it's going to be 0 and 1 for S and R. Again 1, 0, it's 0 and 1 for S and R. When both are 1, it's S is X, R is 0. And when both are 1, S is X, R is 0. So now we have got the K-map. All we need to do is combine the 1's and the X's and find an expression for it. So let's combine these two. So S is going to be X1, X2 prime. And for R, we can combine these four together, where R is going to be X1 prime. Now we have got two expressions for S and R. We can just use these as an input to the NSR latch. And let's draw the circuit for it. Now our S is X1, X2 prime, and R is X1 prime. Now we have got the SR latch with an S input, R input, Q and Q bar. This is actually our Y. And X1, X2 prime means we have got an AND gate. X1 is directly coming in, and X2, it's going to be inverted. And we also have X1, which goes into the R input. But that has to be X1 prime, and that's going into the R input. Now this is all you need to do for implementing an asynchronous sequential circuit with SR latch. If you have any questions related to this, note it down and you can ask me during the question and answer session. And in this circuit, be careful that S and R equals 1 never occurs by this design. So you can find the similar slides, what we have done as an implementation with the Carnot maps and the simplification, then the logical implementation of it. Now, the last part of this chapter is asynchronous sequential network analysis. So if we have something like a complicated circuit over here, it looks like a complicated one, but it's not actually, because we just have AND, OR, and XOR gates. Now, let's consider this circuitry and derive the expression for it, the transition equations and the output equations. Now, let's consider Y1 first, which we have got the upper part of the circuitry, and then we'll consider the Y2, which is the lower part of the circuitry. So Y1 is equals what? It's X1 X2 prime, or X2 Y1 Y2 prime, or X1 X2 Y2. So these are all OR together for Y1. Then Y2 is X1 prime X2 Y1 prime, or X1 Y2, or X2 Y2. And we have got an output equation as Z is equals Y1 XOR Y2 XOR X1. Now these are all the equations that we need to consider for our analysis. For the analysis, we'll start with the transition table. And this transition table, as we have got 2 feedback paths and 2 inputs, we need to have 16 squares. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Then we have got Y1, Y2, X1, X2. Based on these next state equations, we have to plot the transition table. So let's start with the first one. X1, X2 prime. X1, X2 prime. We have to write this for Y1 and Y2, so both of them are on the same table. So I'm going to use colored notation over here. For Y1s, I'm going to use the red color. So X1, X2 prime means these are going to be all ones. Then X2, Y1, Y2 prime. Y1, Y2 prime is the bottom row, but it has to be X2 as well. So X2 is over here, and we just have ones over there. Then we have got X1, X2, Y2. So X1, X2, they're both 1, and Y2 has to be 1, and Y2 is 1 over here, and X1, X2 is 1 over there. So those are all going to be 1s. And for Y1, we don't have any other expression, so the rest is going to be zeros. Now repeat the same thing for Y2. I'm just going to use a different color. So it's X1 prime, X2, Y1 prime. X1 prime, X2 is this column, but Y1 prime is the first two. So those are going to be 1. Then X1, Y2. So X1 is 1 over there, but Y2 needs to be 1, so those two. Then X2, Y2. X2 is 1 on both of those, and then Y2 is there. So that will be 1. Is there anything else that we need to cover or we missed? So let's check. X1 prime, X2, X1 prime, X2, Y1 prime is there. X1, Y2, so X1, Y2, it's over there. But we have to have that one as well because that's also X1. So we need to have those two as well to be 1. And X2, Y2, so X2 is 1 over there and Y2 is there, so those are going to be 1. And the rest is 0. So now we have got the transition table. We just need to identify the stable states, which we need to circle. So the present is 0, next is 0, this is stable. Present is 0, next is 0, this is also stable when it is 1, 1. Present is 0, 1, next is 0, 1, so that's stable. Present is 1, 1, next is 1, 1, next is 1, 1, so those two are stable states. And present is 1, 0, and next three of them are 1 zeros as well. So these are our stable states. And we can derive the the flow table, not the truth table. So the flow table is similar to the transition table, but without the binary numbers, we will just have the letters. So A, B, C, and D, 0, 0, 0, 1, 1, 1, 1, 0, and then again Y1, Y2, X1, X2. So 0, 0 is A, 0, 1 is B, 0, 0 is A, 1, 0 is D, 0, 0 is A, B, C, C, A, B, C, C, and then A, D, D, and D. And once again, we can circle those as well. So A over there, B, C, the stable ones, and the D, D, and D, and those are all stable ones. We can also derive the output table based on the outputs. So that is for Z, Y1, Y2, X1, X2. So the output is Y1 XOR Y2 X1. So XOR function is an odd function. When we have odd number of ones, that means output is going to be 1. So Y1 Y2 X1. So the first one is 0. Second one, it's also 0 because there's no odd number of ones. Then X1 is 1, Y1 Y2 is 0, so that's going to be 1. Then X1 is 1, so that's going to be 1. Then Y2 is 1, so that will be 1. And then Y2 is 1, that will be 1. All that's going to be even numbers, so that will be 0, and that will be 0. So both are 1, that means this is 0 because it's even number. But three of them are 1, that will be 1, that will be 1. And then Y1 is 1, odd number. And Y1 is 1, and then even number, even number. So that's our output transition. Now, we have analyzed up to here, we derived the flow table and the transition table. All we just left to do is, assuming that we start at initial state 0, and we need to go to input transitions 0, 0 to 0, 1, then 1, 1, to 1, 0. So what's going to happen with the state transition and output transition? Now when we consider this, if we start with 0, 0 with the state, and it's A, and then when we have 0, 1, this is actually going to jump from here, there, you can see the arrow, or A to B. Now input is changing to 0, 1, that means this is going to be B, and then our next state is going to be B, so we have to jump down. So our next state is B. At the same time, we start with 0, and when the input changes to 0, 1, we jump to the next one, and then the state changes, we jump down. So that means we start with 0, then 0, and then we have got 1 as an output. Then from B, we have got 1, 1. So B to 1, 1, actually going to jump to 1, 1, which is C. So that means we need to have C, and that will jump down to C. And the output is going to go to 0, from 0 to 1. So 0 and then 1. Then when we have got 1, 0, that means 1, 0 will jump to the next stage, and that will jump to C. So it's going to hold in state C. and we can say that next is C as well, and we can say that the output is 1. Now this is how we analyze the sequential network, and from the slides I just want to show you the similar things. So I just want to repeat, as this looks messy over here. When we have got input transition 0 0, we start from there, from the state 0. When we have got 0 1, we jump to 0 1. So 0 1 will jump down to the next state to 0 1 state. Now we are in 0 1, so that will be B, and the output is 1. And when we are in B, if we have got an input transition 1 1, that will be the next. So we will go there, and then the next state will be 1 1, so which is C in this case, and the output is 1. And when we are in C, when the input comes in as 1 0, the next state is also C. So we just remain over there or stay over there, and the output is still 1. And this is just showing the flow of the asynchronous sequential circuit. Also, we can derive the timing waveform showing x1, x2 for a different states and their output. And the only thing that we need to worry about, as this is changing, and as we already said about the hazards in the previous chapter, this is what is happening. We have got a false output as we have got a delay from one to another. So one of them is arriving later, then that will cause a false output, which is called glitch. That's all I want to say for this chapter and for this course as well. I would like to thank you, all of you, for joining this course, and I hope to see you for next semester or next year for microprocessor course. I hope you enjoyed. If you have any problems or questions, do not hesitate to contact me or write to me, and we'll deal to solve it. Good luck in your exams and good luck in your future career. Thank you.